All right, I actually got a lot of questions this morning, so we'll start working through them. Again, if you got questions, please feel free to post them in the chat. First question was asked about question 55 on the homework. You've got this structure, and you're asked to draw the carbocation intermediate if you run this reaction against HCl. So if you're going through an addition pathway, what's going to happen is that this double bond is going to attack this hydrogen first. This will give you a chloride. Now, it can attack from either side. You can either create the carbocation here or here. This hydrogen is going to get added to one of them. So if you had your carbocation on that tertiary carbon, you're correct. The email got asked, I added a hydrogen. It's probably just their code being nitpicky. So if you draw this into the structure, that's correct. I think if you add the H, it might just nitpick you and tell you that you're wrong, even though you're technically right. It's just the obnoxiousness of the software we're working with. So that was the first question. All right, now a very lengthy strand of questions. 41, 42, 47, 48, 49, 51, 56, 60, 62, 69, 71, 72, 73, 74, 85, 86, 87, 88, and 89. So let's start with 41. So question 4, predict the following reaction and then draw a stepwise mechanism. So we have, starting out with this alkene. Now, this is kind of where it gets kind of weird. H2SO4 will actually add across a double bond. So if you're seeing this, we're going to kind of use context. We got an alcohol. Most likely what we're going to engage in is a dehydration reaction. Sulfuric acid is pretty well known for doing this. So first step in an acid catalyzed alcohol dehydrogenation is that we're going to add hydrogen. And this will give us an OH2 plus, a hydronium intermediate. This will pop off, and we'll end up getting this primary carbocation. Now, we're going to get carbocation rearrangement here from the primary to the secondary, though honestly, this is not going to make a big difference, and we'll see why in just a minute. So when we get this carbocation rearrangement, we subsequently get the bisulfate, the HSO4 minus, to abstract the hydrogen, and I'm going to assume that this is the product. So this is my guess looking at this problem. Now you may ask, why don't you get a subsequent methyl shift? The answer is a hydride shift. There's a barrier to it for a methyl shift or any type of carbon shift. There is a barrier associated with this. Because of that, you typically only get to move one carbon before the reaction completes. Now, there will be some degree of product where this moves over as well, but again, we only get one movement in terms of time before the reaction completes. So again, my guess is for the final product, let's see if I'm right. Yep, thinks I'm right. All right, so now we're just going to start working through the mechanism. So when you draw the structure, it's going to pull the hydrogen off, and we're going to end up with bisulfate. Let's see if you can see that camera angle. Barely, but it's there. So you did end up with the bisulfate. So that'll be the first one, is that you create the hydronium. And I'm sorry, what I'm really curious about is whether or not it makes it to the carbocation rearrangement. So far it's agreeing with me. Oh, it's not going to make you do the carbocation rearrangement. So with this problem, it is a primary. You would expect a carbocation rearrangement. I think for simplicity, they're kind of omitting that step. So what we're going to have is the bisulfate work on this directly. So we're going to skip that carbocation step. They're basically going to do an E2 elimination. And again, I don't think this is what really happens. Honestly, you get the same answer both ways. Now, for this part, you're going to need to draw a hydrogen into the molecule because you need that bisulfate to have something to extract. So let me switch it to the desktop. I wouldn't necessarily agree with this mechanism, but I can see why they're doing it. It does kind of like jump over some kind of irrelevant details. You end up with the H2SO4. Oh. Right, you lose the water too. And that's it for that problem. So again, this is an acid catalyzed dehydrogenation. I understand why they're arguing E2 because it's a primary alcohol. That said, alcohols are pretty good at leaving. So even if you do the E1 mechanism, you're still going to get the same answer because you don't expect that carbon to shift. 42. Predict major products of the following reactions: cyclohexylbromide with potassium ethoxide. Now we're going to play with a little bit of context here. We know that we are dealing with alkenes. It's probably what we're making, so we're probably not making ethers in this case. Most likely what you're going to get is an elimination here. So you're going to get ethanol, the bromide ion, that's how you get rid of the negative charge, and you get the cyclohexene. So major product here is one cyclohexene and ethanol, and that would be it. So basically, it's trading off anion stability. This can't exist in water. It's super, super basic. Bromide can exist in water. It's not that basic. Now, I'm just using water kind of here as a baseline. If it can't exist in water, it's much more basic than hydroxide, which means it prefers the elimination. Something like bromide, though, it's kind of basic, but basic in the sense that it can't accept a hydrogen, just generally doesn't. In fact, HBr is a strong acid. So we're basically, what makes it a strong base is that it's not very stable. Something like bromide is a terrible base because it's super stable. $47. The ratio of elimination and substitution is exactly the same. 26% elimination for 1 bromo, 2 methyl butane, and wow, it should be a space there, and 2 iodo methyl butane, should be another space, and 80% methanol, 20% water, another space, at 25 degrees C. By what mechanism does substitution most likely occur in these compounds under these conditions? Select the best one. So let's take a look at what we have. So 2 bromo, 2 methyl butane. So we have decent leading groups here. Ethanol water's pretty high dielectric constant. So my guess here is that if we're going to do substitution, it's going to be by an SN1 pathway, because we're both creating tertiary carbocations. We're in pretty high dielectric constant solvents. So my guess here is SN1. Let's see if it says I'm right. Okay. So 47 is definitely SN1. Again, a lot of the factors we're considering here. Water's your solvent. That stabilizes carbocations very well. It's got some ethanol, also stabilizes carbocations. We're going to end up with tertiary carbocations that are pretty stable. And even though these are halogens, they are leaving off of a tertiary carbon. 48. What three alkenes yield 2-methylbutane on catalytic hydrogenation? So let's draw the product. We've got 2-methylbutane. And so we can put our double bonds and it's looking for what three alkenes. So the nice thing about hydrogenation is as long as we see like that 2-methylbutane structure in there, we can put the double bond anywhere we want. So we put a double bond there, there, or there. The backbone is the same. Now hydrogenation does not result in any type of rearrangements. The only thing it does is it adds hydrogens. So as long as we have, like, if we draw out our structures and we end up with this, we're fine. So there's 2-methyl-1-butene as an option. That would be that one. 2-methyl-2-butene would be that one. 3-methyl-1-butene would be this one. That just happens to be the answer A for me. For some odd reason on the instructor side, A is always the correct answer. Let's look at the other ones. 2-methyl-1-butene. That's there. 2-methyl-2-butene is here. 3-methyl-1-butene. Wait a minute. Oh, I read the wrong line. Okay, so one of the options it gives is 2,3-dimethyl-2-butene. The reason that doesn't work is it looks like that. And so when you hydrogenate, you're just getting rid of all the pi bonds, and that would be your structure, which doesn't look like that. So actually on my side, it's B for the correct answer. 2,3-dimethyl-1-butene. Already saw it. The 3,3-dimethyl-1-butene also doesn't work because you got this tert-butyl group. When you hydrogenate, you don't lose groups. So basically what you would do is you would draw out what alkenes it's giving you and see if you see the structure in it. So if you're seeing this just without any double, so basically we're just throwing double bonds in there to hydrogenate. If you see your final structure in there, which is double bonds added to it, that will hydrogenate just fine. I think 49 is the next one. Yep. How many alkenes yield 2,2,3,4,4 pentamethylpentane on catalytic hydrogenation? Good question, actually. So let's draw the product. Pentane. It's pentamethyl. There's 5, so we have 2, 2, 4, 4, 3. So the question is, can we throw a double bond in here? And these can't double bond it because there's no hydrogen to remove. So that's gone, that's gone, that's gone, that's gone, that's gone, that's gone. The only one that we can remove a hydrogen from and still preserve these 4 bonds in carbon is this one. So I'd argue you only have one that you can hydrogenate. And that's correct. So yeah, what you do is you look for places where you can eliminate hydrogens. Now, these all connect to a quaternary carbon. There's no hydrogen here to be removed, so you can't form any double bonds here. Same thing about this carbon, this carbon. There's no hydrogen to be removed here, so you can't form a double bond. Your only option is from here to here, because if you look at it, before we hydrogenate, there's a hydrogen there, and there's 3 hydrogens on this one that we can eliminate 2 in order to get our double bond. Uh, 51. On being heated with a solution of sodium ethoxide in ethanol, compound A, C7H15Br, yielded to 2 mixture alkenes of B and C, each having the formula C7H4. So this is elimination. Catalytic hydrogenation, the major isomer B or the minor isomer B gave only 3-ethylpentane. Draw structures for compounds A, B, and C consistent with these observations. So we're going to finish with 3-ethylpentane, which looks like this. And we did catalytic hydrogenation. So if we look at what we could have hydrogenated to make this, if we put a double bond here, I know it's a little hard to see, but this is actually a molecule that's rotated by rotation. So basically, the reason why it's giving you these three ethyl groups bound to the same carbon is that there's a lot of symmetry. So if we put a double bond here, 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 they're all going to be the same compound because by adding that double bond, basically we can rotate it. So adding a double bond here, here, or here, they're all going to be the same compound. So our only other option here is to have a terminal alkene. So we can either have the 2-pentene or the 1-pentene. Again, the reason this happens is that these are three alpha groups bound to the same carbon. There's a lot of symmetry here. If you build it, you can just keep rotating this 120 degrees, and these would all look the same. Now, we did an elimination, and we need to be able to eliminate off of the same carbon in order to be able to make these two. So the pivot point here, the point that they share in common with a double bond, is the second one. This is going to be where the bromine is because basically we eliminated away from the bromine. So if we put the bromine on that center carbon, the only option for elimination is from here to here, which will generate this one, but there's no way we can eliminate this bromine and get a terminal alkene. So we need to put the bromine here in order to get eliminate. So eliminating this using that hydrogen will give you a terminal alkene. Eliminating a hydrogen from the center carbon to that top bromine will get you the second, the 2-pentene. So compound A, I'm going to say is 2-bromo or 2-bromo, 3-ethyl pentane. Yes, it is a chiral compound, but they don't seem to mind, so we're not going to worry with it. And it shouldn't matter which ones you enter for A and B, or for B and C. It's going to recognize that there's probably two answers keyed in for both. Oh, the minor isomer C. So the major we're going to predict will be the Zaitsev product. So this will be the major product, but it makes that distinction. B is the major, C is the minor. This is an anti-Zaitsev elimination. So C, we do actually expect, sorry, I misspoke earlier. We do expect there to be a specific answer for B and C. C is the minor one. This is the one that forms a terminal alkene. They're less stable, and on top of that, this violates Zaitsev's rule. That's correct. All right, 56. Show the overall reactions for the formation of a racemic mixture of 3-bromohexane from E3-hexene. Good lord, their space is missing. 3-hexene by entering the structures of the products reactions in the template provided below. So E3-hexene means the highest priority groups are opposite each other. Now, I had a student ask me yesterday, 1, 2, 4, 2, 4, 6. How do I draw these? What I always start out with is the linear, and I draw it and see if it's E or Z. If it's wrong, I just rotate one of them along the double bond. So this is 3-hexene. If it's E, the highest priority groups are opposite. So hydrogen versus hydrogen. Hydrogen's lowest priority, so our top group. And this group are opposite, so this is the E3-hexene. Now, for the 3-bromohexene, there's going to be a racemic mixture. What they're doing is they're doing HBr. And the 3-bromo is going to place it there. Now, the question is, which of these is S and R? This is the easiest one to work with because the lowest priority group, hydrogen, is in the back. So I can kind of read it as is. So bromine here is the top priority. Between the two branches, the longer one is going to be the higher priority. So 1, 2, 3, this is clockwise, so this is the R, and that's the S. So let me make sure I'm right. And if you get your R and your S's flipped, I mean, as long as you got 3 bromohexane, if your wedges and dashes are flipped, all you gotta do is just flip them and make them correct. Cool. All right, next thing it asks is for the stepwise mechanism. So, for the mechanism, we start with HBr. First thing we're going to get is an attack. Now, we know the bromide is going to end up on the carbocation, so in terms of deciding which way it goes, basically we know we have to finish with the bromine on that carbon. So that'll be our carbocation, and that gives us the bromide ion. And then the last step is just the carbocation attacking the bromine. I think you can figure that one out. All right. 60. So the addition of hydrogen chloride to 3,3-dimethyl-1-butene gives a mixture of 2 isomeric chlorides in approximately equal amounts. Suggest reasonable structure for these 2 compounds of both carbocations intermediate. And it does tell you that it gives you a flow diagram here. So it gives you the overall reaction. And you get attack on the H, and this will give you your first carbocation, which is this structure here. So this is a secondary carbocation. And 1 is just straight chloride attack. So with the straight chloride attack, you'll end up getting a racemic mixture of this compound. So the chloride, both the R and the S. The intermediate for the methyl migration, we're just going to get a methyl shift over, and this will take us from a secondary to a tertiary. And then when we add the chloride back to it, we'll end up with this structure. So you get both the 2-chloro, 3,3-dimethyl-butane. In this case, you get the 2-chloro, 2,3-dimethyl-butane. (62). Part 1 of 4. Draw the major product of the following hydration reaction. So hydration reactions, these are Markovnikov reactions. And you got that nice high symmetry 2-ethyl butane. So when we add the water to it, end up getting a tertiary alcohol. So that's part one. Now, in terms of the mechanism for how this works, first step, we're going to have our double bond attack the hydrogen on hydronium. And this will give us our carbocation intermediate and water. The next step, when the water is going to attack the carbocation. And so we'll end up with this hydronium complex. And then we'll have another water molecule come by, and what this water molecule will do will be extract a hydrogen, and that'll get us back to the alcohol and our starting hydronium ion. So I'm assuming that's what the next steps are. I really don't want to like drag through like drawing every single one of these. 20, 21, and 22 on the packet. So yeah, let me get through the homework and then I'll get to those. 62, 69. I've got about 8 more to go. 69. Predict the following reaction. We have borane, BH3, and ether. This is actually just walking you through the mechanism of hydroboration oxidation. Hydroboration oxidation is kind of a weird reaction. But what you end up generating is this boron intermediate. And it's going to force you to put the formal charges on here. Okay, so it's not even going to go that far. Okay, so basically what it's trying to get you for this one, it's an intermediate step in the reaction, so you're going to get the BH2 and the H. And this is how you get the anti-Markovnikov product. I thought it was going to make it go through the intermediate first. But what you do is you get BH addition across. So this attacks, and then if you go look in the notes, there's a mechanism that explains how this ends up getting the hydrogen over. And then from there, yeah, that's step one is you do the, you add the BH, and then I think it makes you walk through the rest of the mechanism. Let me check. So yeah, you're just going to have, sorry, I'm skipping through the answers because I'm getting very tired of like trying to fight with their drawing program. So you get attack on the BH3, This will produce a intermediate, and then what will happen is that one of your hydrogens will slide over, and you'll end up generating this complex here. '71. So we've got the reaction of potassium iodide and H3PO4. Phosphoric acid here is just a protonating agent. It's there to supply hydrogens instead of working with HI. Basically, you're making hydroiodic acid. So this is kind of taking the long way around. What's really going on with this is that you're forming HI. It would be the same mechanism you expect for HI. So what's going to end up happening is, first step is we're going to get abstraction of the hydrogen, and this will give us our carbocation intermediate. And then our carbocation will attack potassium iodide. So your organic product is this complex. Your inorganic product is your H2PO4 minus 1 for the first step in the mechanism. And then what'll happen from there, you just have the iodine attacking that. That'll give you this structure. It's kind of a long way to do this type of problem, but basically that's effectively what's happening. This pulls the hydrogen off, that's your organic, that's your inorganic, and it's going to make you draw it all out. '72. Hey, Dia. Suggest a reasonable mechanism for the following reaction. Be sure to include all charges and lone pairs. So we have hydration of 1,2-dimethylcyclohexene and I do like that they're using symmetry to make these a lot easier to draw. Yes. So after I get done with these questions, I'll answer the questions on page 20, 21, and 22, and then I'll answer your questions. All right, so it starts you off with this complex, and you got your H3O+. The heavier molecular weight, we get attacked there, and it's not going to require you to do stereochemistry. Basically, you can end up with racemic mixture. So your higher molecular weight compound here is the carbocation. The water is then going to attack that carbocation, and we're going to end up with the OH2 complex. And then the OH2 complex will lose a hydrogen to the water. So we draw the hydrogen in there. That's how we'll end up with the 1,2-dimethylcyclohexanol. '73. Bromination of Z3-hexene yields a racemic mixture of 3,4-dibromohexane. Please provide a detailed mechanism for the formation of 3S, 4S, and enter, specifically showing Br2 addition occurring from the top face of the alkene. All right, so in the notes, it goes through how this mechanism works. But you actually go through a cyclic complex. So the double bond is going to attack. The bromine is going to come down. This will break off this bromine. And our intermediate here is a cyclic bromo complex with bromide. And the big thing with this is to specify the stereochemistry. In this case, it's going to want the two wedges. But you basically end up with an epoxide, where instead of oxygen, it's bromine. What will happen is subsequently the bromide will attack this carbon, break this bond, and this is why this is a anti-addition. They have to go from opposite sides of the molecule. Basically, this bromine squats is on top, and the only way to get attack is to go from underneath because that's the only place where there's any space. $74. $74 is the exact same question. Instead of having the cis, now you have the trans, but it's going to follow the same line of reasoning that you're going to go through that cyclic complex. And again, the big thing, if you switch from cis to trans, is making sure that you've got the wedges and dashes drawn correctly. Personally, I like to keep the bromine in plane. So since they're trans here, they're going to look like they're trans in this intermediate. For the other one where this is down, it's going to look like that. But with these, you definitely have to specify the stereochemistry. 85. I got 3 more. 85. Draw the structure of the organic intermediate that forms before workup of the reaction of 1-pentane with ozone. So go into the notes. This is going to show you the actual mechanism. So in the notes, it actually draws out what that intermediate is. So I'm going to recommend you go to that. I'm not going to go through a lot of that because it is like worked out pretty explicitly in the notes. 86. Draw the structure of the major organic formed by the reaction 1-methylcyclohexene with ozone followed by dimethyl sulfide. Again, keep in mind dimethyl sulfide here is just to decompose the intermediate. And so the ozonite intermediate, again, the notes explicitly state what this ozonite intermediates are. I would recommend going to that to look up that answer. In terms of the final product, the 1-methylcyclohexene, you always cut through the double bond. So we got 1, 2, 3, 4, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7. Our second carbon, we cut the double bond, that becomes an oxygen. Our 7th carbon here, we cut the double bond, you get an oxygen. So this actually has, let's see here. No, septanal. So this is 6-oxo-septanal that you'll end up forming. But again, with all ozonolysis reactions, you cut right through the double bond and you put an oxygen in place of those double bonds. $87, $88, and $89. Almost done. 87 is actually giving you the ozonite intermediate. Draw the structure of the major product formed from the reaction of the ozonite with zinc and water. This is just a decomposition reaction. If you look at it, that ozonite comes from basically taking this double bond and converting one bond to an oxygen and the other to a peroxy group. So the way you would backtrack this out, this is your starting alkene. Cut that again. And it's actually the same product from the previous reaction. Write the major organic problem when Z2-pentene and bromine reacts with bromine. If 2 stereoatoms are formed, draw both. So we've got Z2-pentene. 1, 2, 3, 4, 5. And we're going to add bromine. Now the question is, how many do we form? So these are definitely both chiral centers. The thing is that it's a fixed, it's an anti-addition, which means we only end up with enantiomers. So we're going to end up with 2 enantiomers. So in terms of how many stereoisomers are formed, there's going to be 2. Are stereoisomers formed? Yes, there are 2 of them. And it's going to ask you for the 2R, 3R, and the 2S, 3S. We know that they have to be anti. So the easiest way to do this, one's up, the other's down, one's down, the other's up. All we need to work out here is which. So in this case, if we look at this comp, I like to work with the wedges first, the easiest to see because the hydrogen's in the back. So that's highest priority. Second, because it's got a carbon, it's the longest chain, it's got a bromine. 3, so that's S. And since I flipped it over here, it's going to be R. If I look at this one, this is highest priority. This carbon has a bromine attached to it, this doesn't. So this is the second priority, third priority. So it goes around, this is R, this is S. So it asks you for the 2S, 3S, it's the one with the wedge up, wedge back. And then for the 2R, 3R, it's the one with the wedge back, or the dash back and the wedge up. Last one, 89, for this one email, for 89. Products of 1 butene with peroxyacetic acid and dichloromethane and 2 stereoisomers are formed. So we have 1 butene. And the question is, if we form the epoxide, do we have stereoisomers? So if we take a look at the epoxide, this carbon here is not chiral because there's 2 hydrogens, but this one is. It's got a hydrogen, an oxygen, a carbon, and an ethyl group. So we definitely have a stereoisomer formed here. So we do have to draw both. So we're going to have one where the oxygen is up, and one where the oxygen is down. So yes, there are stereoisomers formed, and there are 2 of them. The S and the R, again, I like to work with a wedge because it's the easiest. The hydrogen's back. Oxygen's highest priority. This carbon is bound to another carbon and 2 hydrogens. This carbon is bound to an oxygen and 2 hydrogens. This oxygen is going to take priority, so this is the second highest, third highest. That's clockwise, so that's the R conformation, which makes that the S conformation. For some of the multi-step reaction problems, it's like the one on page 18, one step goes to an elimination product. Do we assume it is E2? Yes. Pretty much for all of these, we're going to treat them like they're E2 reactions. Generally speaking, we're not going to be dealing with any of the primary eliminations. They get kind of messy. So since these are, well, actually, even if these go through like E1 intermediates or E1 reactions, because some of these reactions are tertiary, they end up not rearranging. So I would say, yeah, treat them like E2, but honestly, practically, you shouldn't see any type of carbocation rearrangement. All right, page 20. All right, so page 20 is actually a lot easier than it looks. So we have this halogenation reaction, and we want to know, did we get the Markovnikov or anti-Markovnikov product? And this is actually really, truly, honestly, a logistical issue when you do these types of reactions is, did you make what you thought you made? So it gives you both the 1-methyl, 1-chloro-1-methyl, and the 1-chloro-2-methyl, and asks which one did you make? And there is a lot of junk in this spectrum, particularly if you look around the 1.5 ppm, there is a ton of peaks. But the thing is, there's a singlet. And the singlet here is the tip-off. So if you look at the NMR spectrum about, let's see here, 1.3 ppm, there's a singlet with 3 carbon or 3 hydrogens. Well, there's only one way to get that, and that's with a methyl group. And if we look at these 2 molecules, this is the only one that can produce a singlet because this is the only one where there isn't an adjacent hydrogen. So this can't happen because this would end up being we got a hydrogen here, this would end up being a doublet, multiplet, 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 multiplet. So even though we've got all this hydrogen NMR stuff in there, really the tip off there is that you have a singlet. And the only way to do that is if you got the Markovnikov addition. All right, page 21. You want to know what you produced, and you're going to figure it out by seeing how the NMR spectrum changed. So if I look at the carbon-13 NMR, I have 6 unique signals. And I'm also going to have, so what I'm looking for here are 2 things. I'm looking for the number of signals. So in terms of the products, bromine, dibromo, and we've got the tri-substitute. So if we look at all of these are 6 unique carbons. There should be 6 unique carbon-13 signals, and that's what we see in the carbon-13. So the carbon-13 is not going to do us any good. But if we look at the hydrogen, there's 1, 2, 3, 4, only 5 peaks that are there. So if we look at this one, there's 1, 2, 3, 4, 5. Oops, that's not. Hang on. There should be 6 H&MR, 6 1H&MR signals in this molecule, and there's not. But if we look at this one, there's 1, 2, 3, 4, 5. And here there's 1, 2, 3, 4, 5. So off the bat, we can pick this one off because it's got too many peaks. So now we look at the areas. 1, 1, 2, 2, 2, 1, 1, 1, 2, 2. And if we look at the areas and the peaks, we've got 1, 1, 2, 2, 2. So we've got 3 2s, 1, 2, 3, and 2 1s. So this is the only one consistent with the 1H in terms of area. So I didn't know anything about the splitting patterns. All I need to know was, does it produce enough hydrogen peaks? And if they are, what's the correct area? Now, page 21 is a bit harder than what you'd ever expect to see on the exam. But that's how you solve it, is you start looking at the number of hydrogens. All right, 22. I like 22. So for 22, the trick here is also looking at the number of signals. So we've got 2 options for how the substitution would occur. Option 1 would be I'll tell you what. Oh man. So if we look at the 1H NMR, there's only 3 signals, which means that we can't have more than 3 unique positions. So if we look at this molecule, there's peak here, peak here, peak here, peak here, peak here, and a peak here. So we expect to see 1, 2, 3, 4, 5, 6 1H NMR signals. If we look at this one, there's a mirror plane running down the center. So we're going to have a signal from this, a signal from this, because these 2 hydrogens are equivalent, they're going to have the same chemical shift, and we're going to have these as another shift. So with this, we only expect there to be 3 unique NMR peaks, and if we look at the 1H NMR, that's exactly what we see. There are only 3 unique chemical shifts. So the top one here, the one that where the bromine substitutes in the center, that's the one that's consistent with the NMR spectrum. All right, so I got one more from the emails. Question 26 from the study guide. So why does CN create an inversion of symmetry? CN creates an inversion of symmetry only if you're working with Tosyl chloride. So I'm assuming it means page 26. Yeah, you're welcome. Yep. So for page 26, you're looking at a synthesis, and the easiest way to do this synthesis is, the first step is to go through halo hydrogen addition. And what this will do is it will give you the trans product. And for ease, I'm going to write the alcohol going backwards and the bromine coming up. Now, if you just approach this with KCN, and you could do that, you need to do this in something like diethyl ether and hope for the best. because what we need here is an SN2 pathway. And the SN2 pathway ensures that we get inversion of the chiral center. Well, another easier way to do this with alcohols that we don't have at our disposal with halogens is to first work with Tosyl chloride. So what Tosyl chloride does is it binds to the alcohol. And Tosyl chloride is an excellent leaving group. If you need something that's going to proceed through an SN2 pathway, Tosyl chloride pretty much guarantees you, at least from what we've been able to discern as instructors, about 80% of the time it's going to be an SN2 pathway. So by doing the Tosyl chloride and then adding the KCN, you're pretty much guaranteeing that this is going to proceed through an SN2 pathway. But you could run this with just straight potassium cyanide. I mean, it's not impossible. But the reason why I advocate this, if you look at a previous discussion board, it asks about the different reagents. So PBr3, SOCl2, PlCl2. KCN is one of them, and asks, is it a stereospecific reaction? And the answer is no, it's not a stereospecific reaction unless you run this under conditions where this would be a low dielectric constant solvent, low temperature, where you can ensure that it's going to go through an SN2 pathway, because cyanide is going to act like bromide, like chloride, like hydroxide. It's going to try to substitute, and it doesn't necessarily pick an SN1 or SO2 pathway when it does it. By working with Tosyl chloride, you're ensuring that you're getting that SN2 pathway. There can be carbon-cation rearrangements. Keep an eye on them. Generally, even the textbook kind of stays away from carbocation rearrangement problems with Markovnikov's rule. So in general, just keep an eye on it, but to be honest with you, it starts getting into levels of way too complicated for what we're trying to assess. So what you'll generally see is we stick to secondary and tertiary carbons when we work with Markovnikov's rule. So yeah, I wouldn't worry too. Be aware of it, but don't worry about it too much. You're welcome. Oh yeah, definitely. Especially if you understand the problems of the study packet, you'll be more than set for the exam. You're welcome. All right, that seems to kind of be it for questions. So again, if you have any questions, please feel free to email them in advance. As you saw at the start, definitely go through them. And I will see you all Monday.